Okay, so accumulation mode, clearly transistor is off. Okay, it is not on, mainly because the source and drain are definitely separated by a P plus region. There is N plus, there is P plus because everything is attracted, and there is N plus again. So it is not connected to each other. So next we will slightly change this. Okay, so I'll remove all these extra things. Okay, so next again we will apply a voltage, and this voltage Vg, very small. Okay, let us assume it is a small value but a positive value. Previous case it was a negative value. I'm going to apply a small positive value. Okay, so what is that going to do? Again, now my focus is on the channel region. Whenever my transistor becomes from conducting to non-conducting, okay, the channel region is the one that is going to somehow determine that condition. So we will look at the channel region again. Now I am applying a small positive voltage. Okay, now what will happen in the channel region? First is the holes. There were a lot of holes through the substrate. In the channel region also holes were there. Okay, but now because of the positive voltage, the holes will get pushed away. Okay, there will be very few holes in the channel region. So what will happen here is, I'll write that if you want. Holes, the holes are pushed away. Normal, you apply a positive voltage, holes are positively charged, they will get pushed away. That is normal, right? But also the problem is, since it is a very small value of positive voltage, okay, small positive voltage is not strong enough to attract what? When I apply a positive voltage, what will a positive voltage attract? It will attract negative. What is negative? Electrons. Okay, so the small positive voltage is not strong enough to attract minority minority electrons. Just from this analysis we saw that even though it is a p-type substrate, okay, the concentration of electrons is not zero. Concentration of electrons is very small. It is around 10 power 17 per centimeter cube. Okay, it's very small number. 10 power 17 per centimeter cube is very small, because in silicon, for example, the number of atoms is 10 power 23 per centimeter cube. So 10 power 7 divided by 10 power 23 is 10 power minus 16. That is not even in femto. You have nano, you have pico, then there's femto. I think 10 power 18 is atto. So it is around 100 atto per centimeter cube. Very small. Sorry, not 100 atto. It's compared to silicon, it is very small. Okay, so this very small positive voltage is not strong enough to attract those minority electrons which are spread through the substrate. That is, in this p substrate there will be electrons all over. So what happens is, in this region, that is the channel region, Okay, holes are also gone, electrons are also not there. Generally, when you look at any substrate, okay, it might be p type or n type, there will be some holes, there will be some electrons. Here what happens is the holes are getting pushed away, so only electrons are there, but because they are so low, okay, 10 power 17 per centimeter cube only, nothing extra is getting attracted because the positive voltage magnitude is very less. So what happens in this region, that is the channel region, it becomes a depletion region. Depletion means that there is no mobile carrier. So it doesn't mean that the silicon itself has disappeared. That cannot happen, okay? Because silicon is a structure. It has atoms, it has bonds. What happens is the free charges. That is why it is saying as mobile carrier. Silicon is not a mobile carrier, okay? Silicon is a atom. The electron or the hole, these are the mobile charge carriers. Atom or the holes are the, sorry, electrons or the holes, these are the ones that move, okay? The silicon atom itself cannot move. There is no way silicon atom can move. That requires much higher voltage, almost like you should see the IC melting. And this happens, of course, for example, if ever your computer has been repaired, okay, if something is not working, it could be that because of very high heat, the this thing has melted, some circuit or something has melted, and it stops functionality. You cannot do anything, you just have to replace it. But this is not the case here. Here the mobile carriers means electrons or holes, that is just a normal mode of operation, okay? So in this second mode where we apply a small positive voltage, what happens is the channel region is depleted of mobile carriers, and that is why this is also called as a depletion mode of operation. Okay, this is the depletion mode. That is from the channel region, we are hardly having any mobile carriers, and because of that, still the source and drain are not connected to each other, and transistor is it is still off. Okay, we cannot have a connection between source and drain. There is no way that we can connect the two terminals in this mode of operation. So this is the second mode, depletion. We are slowly going towards on. Okay, when do we turn it on? When we go for higher value of voltage, and that is what we will see in the next mode of operation, which is also the last mode of operation. Okay, so now we will give the highest possible value in all digital circuits. Like I said many times, remember only two values of voltages. In between, it has to change, meaning it will go from 0 to 2 or 2 to 0. It has to go through a range. Okay, but at a steady state of operation, okay, there are only two particular values for the voltages. One is ground, or which is the reference value. We will take that as 0, and everything is with respect to that reference. Okay, and the power supply is generally called as VDD, and we many years ago it was operating at 10 volts maybe in the beginning, then it eventually came down to 5 volts, Right now it is lower than that also. It depends on the circuit, maybe 2 volts, maybe 1 volt. But 2 volts is a normal number. Today for many circuits, it might be operating at 2 volts. So your battery also, your laptop for example, is having a charger, okay, that is taking the 230 volts from our mains, and then it is converting that to around 5 volts, and that is what is supplied to the PCB. And the PCB will have one more transformer. Before it is given to the IC, it will generally be converted to a lower value also. That depends on the circuit. It might be 3 volts, it might be 3.3, it might be 2, I don't know. But let us assume that it is 2 volts for now. Okay, so that is what we are giving to the gate voltage equal to VDD I 2 volts. So nothing bigger than this for our circuit. This is the maximum positive voltage. Now from common sense, if I give a positive value, okay, positive will do two things. One is it will repel all positives, okay, and it will attract all negatives. Both the things are happening simultaneously because of the positive voltage. So this is p-type substrate throughout. First is positive voltage, okay. So again, the actual current conduction cannot happen. Only thing is there will be a electric field. Whatever voltage we have, okay, if you remember, there is an equation E approximately equal to V by L, right? And this electric field is what is attracting the electrons, but they cannot participate in current conduction. So electric field is in downward direction, which means that the positive charges are experiencing a force in this direction. So they will all get pushed away, okay? And the same electric field will be attracting the negative charges towards the channel region. So I'll remove this electric field. This is just for explanation. Now we can redraw this channel region, and in the channel region we see that the electrons come and accumulate. In the previous case, the voltage was very low, so the electrons were not feeling it. Okay, they were like, oh, it's there, but it's just too low, I'm not going to go. But now the voltage is very high. It is pulling all of them strongly, and from through the substrate it pulls them because there are electrons. Plus, there are also electrons, very large number of electrons on these two sides. So all of them get pulled a little bit, okay, and they all directly come and sit directly in the channel region under the gate terminal. They cannot go anywhere else because of the insulation, okay, and they're attracted. This is like, for example, if you have a magnet and if you have some metal pin or metal filings, etc., all of them will get attracted and they will sit on the surface of the magnet, right? They can't go into the magnet because the force is not that strong. Same thing here also. They will all come and sit, okay, directly under the channel region. Now they are ready for your command. And the most important thing is this, okay, looks like I have basically, if I redraw the transistor, okay, it looks like this now. I have formed the connection between the source and the drain. Source is N plus, drain is N plus, and middle also I have formed this N plus region. I didn't fabricate it, okay. The electric field or the electrical effect of the gate voltage pulled the electrons into this region. Now it might look like this. Source and drain are connected through the channel region. Most importantly, okay, transistor is finally, the transistor is on, or the source and the drain are connected to each other. Switch is closed, okay? And also the particular physical phenomenon that enabled the transistor to be considered on is called as Okay, the substrate region itself, okay, it's a p-type substrate, and it has inverted from being a p-type substrate with majority holes. It is now not everywhere, okay, I didn't say everywhere, only in the channel region. Okay, inversion of the substrate, I can add this if you want, inversion of the substrate in channel region. Not everywhere, definitely, that's not possible. But the channel region is one which is important to us, because that is where the current conduction or the connection between the source and the drain has to take place. And that particular region, it has inverted. Originally, it was a p-type material. Okay, it was a semiconductor of type P, and now it has inverted into n-type material because of the gate voltage. So now the transistor is considered to be on, and this mode of operation is also called as inversion mode, and this is the most important mode for current conduction. Okay, only in inversion mode of operation the transistor is considered to be on, that is source and drain are connected. If you apply a voltage, current will flow. Up to this point there is no connection between source and drain. Now source and drain are connected, and as always, do this exercise for a PMOS transistor. Tell me what will be the gate voltage and one example. Okay, and what will this diagram look like for inversion mode of operation. And remember that in CMOS transistors also, this is digital circuits. So the most negative voltage is only 0 volts. Okay, so you can't go to minus 2 volts or minus 5 volts. Those voltages are not available in digital circuits. So the negative most voltage you can give is 0 volts. Positive most voltage you can give is 2 volts. So relative to each other only, our circuits will be operating 0 volts, 2 volts, or 5 volts, or whatever. Okay. So this is the most important mode of operation, which is called as inversion mode of operation. And in inversion mode, okay, the channel is formed, conduction takes place. So now we are looking at one very important definition called as the threshold voltage. And okay, so it is some voltage. Okay, it is going to be some value, some volts, maybe 1 volt, 2 volt, etc. And this number is very important in terms of the numericals and everything else. So we'll just try to understand what is the meaning of this threshold voltage. Okay, it is the okay. So one statement might seem a little complicated or confusing, but don't worry too much. We will understand it. It's very simple to understand. Okay, it is a voltage. That is the first thing. It is some number, and it will be some number for a NMOS transistor. It will be some number for a PMOS transistor. But what is the meaning of this number, right? Now we are talking about these modes of operation. We have accumulation mode, that is completely useless. We cannot have any current conduction. We have depletion mode, that is also not very useful. We have inversion mode. Now inversion mode is the one that is interesting to us because here the transistor is on. Now the question that you might ask is, how on is on, right? Like it's not like a perfect this thing saying how many electrons should be attracted to the channel region. So if I redraw this diagram, okay, let us assume, okay, 0.2, we said that almost nothing. We increase it little bit more. I go to 0.3 volts, right? And for 0.3 volts, somehow if I count it, that is if I count the concentration of electrons in the channel region, I am getting 400 electrons per centimeter cube. It's not zero, right? I'm getting 400. But is it good? Am I happy with 400? Maybe yes, maybe no. Okay. So the question that we have to ask ourselves is, now 400 is the concentration of electrons. So you can say that maybe now source and drain are connected, but it's a very thin connection. How thin is it? Only 400 electrons per centimeter cube. 400 is very small number for current conduction, because if you remember, there is one equation. There are many hundreds of equations for current. One of the equation is I equal to Q N. This is one equation, okay, and in this equation N is the number of charge carriers, or the number of particles carrying the charge, and that is 400. Now 400 in normal this thing, maybe when I was growing up 400 rupees was a big number, but today everything starts at 500 rupees only. You can't do much with 400, but still in terms of this equation, this Q, right, is 1.6 into 10 power minus 19. So when that gets multiplied with 400, your current is going to be in 10 power minus 15 amperes. 10 power minus 15 amperes is very low. Okay. You might ask me, what is a good current? Okay. For example, if you look at these plug points, they have a current rating. So they are, maybe the ordinary plug point will work up to 5 amperes. If you look at some of the more powerful ones in your house, maybe for air conditioner or geyser, it will be 15 amperes. Like that for semiconductors also, current value is important. Generally, for all our purposes, the single transistor current, that is the current flowing through a single transistor when it is on, okay, might be in the milli or microampere range, because it's one transistor, right? It's a very small value. But here, if I use this equation, I am getting 10 power minus 15. That is a useless current. Okay, so this value of Vg is still not enough. Let me increase it more. Okay, and say I go to 0.4. Now suddenly this might jump, okay, from 400 to 4 e power 6, and this is definitely higher, right? So then the question now comes, if you keep increasing Vg, your concentration, minority carrier concentration, is going to keep increasing, that is for sure. But when do you stop? When do you say, okay, enough, this much is enough for current? If I have this much amount of carrier concentration, I can get a good current in milliampere or microampere. That is the question that this statement is trying to answer. That is the voltage given to the gate terminal such that the number of, so this P sub, say it is 10 power 15 per centimeter cube. Now this definition tells us that if I put Vt here, Okay, that is, I have put the threshold voltage value. Then I am going to get in the channel region, I am going to get the same concentration of electrons, not of holes. If you don't do anything, only already hole concentration is 10 power 15 per centimeter cube. But according to this statement, what this means is, if you apply this much amount of voltage, that is the threshold voltage value, okay, you are going to get that much amount of electrons in the channel region. What is that much? It is the concentration of the majority carriers in the substrate, which is 10 power 15, and I'm getting 10 power 15 per centimeter cube of electrons. That is what this statement means. So what basically it means is, if you apply threshold voltage, okay, you're going to get enough number of carriers for current conduction. This is a good number. Any above this is acceptable. Anything below this is not acceptable. That is the most important thing to remember. Okay, if you want, I can write that here also. I'll remove this statement. For example, NMOS, okay, NMOS threshold voltage may be 0.6, maybe you will see a numerical where it's 0.45, 0.5, whatever. But one thing is, for a NMOS transistor, it will be a positive value, because NMOS transistor, we looked at the structure, we looked at how to attract electrons. You can never attract electrons with a negative number, right? It has to be greater than 0, okay? 0.1, 0.2, maybe not enough. What will it be? It has to be a positive number and significantly large, maybe 0.5, 0.6 volts. So maybe it is 0.6 volts for a NMOS transistor. Hence, this is the important part. Any VG greater than VT, NMOS is considered on. Okay, this is the condition for on, very important condition that we have derived qualitatively. We will derive more details also. But any value of gate voltage, okay, that you can apply beyond threshold voltage. I am saying threshold voltage is 0.6. Okay, you can apply 0.7, 0.8, all that is fine. I am very happy with all those numbers above 0.6. Okay, how much above can you go? Can you go to 100 volts? No, you cannot go to 100 volts, because our power supply might be 2 volts or 3 volts. So anything above 0.6 all the way up to 2 volts is very good. I am very happy. Okay, I am not greedy saying no, go more, no need. Anything above VT is fine. Okay, but anything below VT, not fine. We will never calculate current if I am finding that in some particular numerical, for example, the threshold voltage of the NMOS transistor is given as 0.5 volts and the gate voltage is 0.2 volts. Okay. The supplementary examination. Hope I never have to see you as any of my students for the supplementary course. Pay attention, listen, okay, and finish it off in this regular semester itself. So what I was saying was, VT, any VG greater than VT, okay, and if VG is lesser than VT, don't have to calculate. There's no need for you to calculate. Okay, if the gate voltage is lesser than the threshold voltage, the NMOS is considered off. There is no calculate. If you're part of a numerical problem where they have given you multiple values of VG, and for one of the conditions you're finding out that this is true, that is VG is lesser than the threshold voltage of 0.6 or whatever, directly you can write IDS equal to 0. You don't have to calculate the current. Okay, that is a separate mode of operation. Maybe sometime we will discuss it very briefly, called as sub-threshold conduction. Okay, as I said, nothing is 0. Every time some current will be flowing, but we will assume that it is 0 and we don't have to do anything for that part. Okay, so since this is important, I will also write these conditions for a PMOS transistor. So we will see the same things for PMOS also, just the conditions, not the whole diagram. So that side is NMOS, okay, not general, even though it says threshold voltage, that side is NMOS, this side is PMOS, okay, and because of the structure, because of the charge carriers, etc., PMOS PMOS threshold voltage will be lesser than 0 volts. Now, definitely, you can ask me, okay, since the beginning of this class or even before that, you have been saying only two voltages, 0 and VDD. Suddenly, if I want a negative voltage for PMOS transistor, where will it come from, right? Good question. We will answer that shortly, but just remember for now, okay, threshold voltage of PMOS transistor will be a negative number. In this thing, for example, suppose they give you, okay, if they give you the magnitude, they say threshold voltage for the PMOS magnitude is 0.5 volts. When you are using that in the numericals, you have to add VT P equal to minus 0.5 volts, because from the structure we have seen that if you apply positive 0.5 volts, you can never attract holes to the channel region. It's a positive number, they will get repelled. So it has to be a negative number only. Okay, that is the first thing. It will be lesser than 0 volts. Then the condition, when is it on, when is it off? Okay, so now I'll mention one thing. Again, I will mention this a few more times as long as we are doing current calculation. We have two types of devices, and NMOS is easier for us to understand because it is a positive voltage device, meaning that the gate voltage has to be greater than 0 electrons, and it's similar to metals in that way. Okay, PMOS, it is exactly opposite. So what my recommendation is to all students is, you remember the conditions for NMOS very correctly. Okay, remember it clearly, don't get confused there. When you are working with a PMOS device, just invert every condition. Okay, NMOS on means PMOS off, NMOS off means PMOS on. That is the most important thing to remember. That is the easy way to remember also. You don't have to remember two separate sets of conditions. Remember these conditions correctly. Okay, VG greater than VT, NMOS off. Now, if you want the condition, suppose you are working with a PMOS device, what do you do to that condition? VG greater than VT, PMOS is off. Okay, don't have to calculate the current. Gate voltage is greater than the threshold voltage. Okay, which means that suppose threshold voltage is minus 0.5 volts and the gate voltage is 0 volts. PMOS is off. It cannot attract any charges. Okay, it will not be conducting. And VG, okay, that condition, same condition here and here, VG lesser than VT, VG lesser than VT. Okay, exactly the same, but only the effect is opposite. Whatever effect was there in NMOS, VG lesser than VT means effect on NMOS is off. VG lesser than VT, what is the effect on PMOS? PMOS is on now. It will be conducting. That is, the channel region will be formed with enough number of holes, and the source and drain are connected together through the channel region. So this is the condition for the turning on of PMOS transistor. That is the NMOS transistor. Okay, everything is dependent on the threshold voltage Vt. So very important number. Okay. So next, okay, so one question that is still pending, NMOS is somewhat okay, because we want positive voltages of Vg, but for PMOS transistor, we want a negative voltage for Vg, but in the circuit we don't have that anywhere, right? We have only positive voltages, or we have zero. Zero is the negative most voltage. So how do we get rid of that particular this thing? In Okay, so how do we solve that problem? We don't want to introduce a negative voltage. That's not possible at all. Digital circuits have no concept of negative voltage, absolute negative voltages. The simple way to do that is use the source terminal. Now every transistor has three terminals: source, drain and gate. Forget the bulk part. Okay, it's not under our control. We can control source, drain and gate. So anytime you are giving a value, or you are measuring something, it is with respect to the source terminal. So therefore VGS equal to VG minus Vs, and VDS equal to Vd minus Vs. That is, this is the simple voltage reference formula from network analysis or any other subject. VGS and VDS. This is how we can get negative voltages for Vg. How do we do that? We just have to make sure that Vs is at a higher value. That is, with reference to Vs, Vg might be negative. That is, if I put Vs at 2 volts. Okay. So for example, suppose this is the connection that I do. I have only two values. You connect those two values. Vs you connect to VDD. Okay. So maybe this is your 2 volt. This is your 0 volt. Therefore, VGS equal to minus 2 volts. That is how we can get negative values. 0 minus 2, we will get minus 2 volts. And this is how we can get a negative value for PMOS transistors. Positive value NMOS transistor, that is normal. We don't have to worry about that. We will get that automatically. But this is the main way. There is no source, negative source is not there. So this we will follow from now onwards. We will try to measure everything with respect to the source terminal. That is, we have gate voltage, drain voltage. Instead of just calling it VG and VD, okay, we will just call it VGS and VDS. So far we have been only working with VGS, right? We have not seen the VDS. Next we will see what is the effect of this drain voltage on the transistor operation. Okay, so this we have already discussed. So far, this is what we have been discussing. The gate voltage, the main responsibility of the gate voltage is to create a inversion region. Okay, and whenever this inversion region is created, the transistor is considered to be on. But now my question is, the transistor is on, right? But is the current zero or non-zero? That is, what is the value of, suppose I have VGS greater than 0 for a NMOS. What is the value of IDS? Is it going to be 0 or non-zero? And for that, okay, we have to look at the drain source voltage, because the current is IDS. IDS means it has to flow in the horizontal direction. Maybe I'll redraw the cross section. So this is the picture. Okay, I have the NMOS transistor. I have applied 2 volts, and since the source is grounded, VGS is with respect to the source. So some 2 volts power supply I am applying to the gate terminal, and since generally 2 volts is going to be more than the threshold voltage, definitely the channel region is inverted. It's no longer p-type substrate. So this picture we are familiar with now. Okay, but now my question is, can I say that current is there? Or definitely it is on. Okay, but if you remember the definition for the current, again we have a different equation for current. This time I am going to use I equal to dq by dt. So q as always represents some charges somewhere. Okay, those are these charges. These charges are mainly attracted by the gate voltage, because this is in a vertical direction, right? So because the gate voltage electric field is in a vertical direction, all the charges are getting attracted vertically and come and sit directly under the gate region. That is our inversion, wherever inversion has happened. But now if they are just sitting, okay, this is going to be 0 because they are not moving. Dq by dt, that is rate of change of charge with respect to time, it is not changing. My VGS is fixed at 2 volts. It has attracted some amount of electrons. They are all sitting in this region, but they are not moving. They are all attracted. Like that magnet picture is very useful. Suppose you have a iron pins and you have a big magnet. To bring them close together, all the iron pins will come and they'll sit right on the magnet. Here also they will come and they'll sit right under the channel region. They'll sit right under the gate terminal, but nothing is moving, which means that dq by dt is 0. It is on, but there is still no current. How do we get the current? That is why we have the drain source voltage. Now this drain source voltage is in the horizontal direction. This electric field, because it is between these 2 terminals, this electric field, okay, this is the E electric field between the drain and the source. Now that electric field is there, it will move the electron in the horizontal direction, and we will have some non-zero value. Now is when the current is flowing. So just by making the transistor on, we cannot say that current is there. Current will only come when I have a non-zero value for VDS. If VDS equal to 0, then definitely current cannot flow. That is the second thing to remember. IDS, okay, somehow it has to depend on drain source voltage. If there is no voltage between drain and source, there will be no horizontal movement because they are at equal potential on both sides. There's no reason for the charges to move, which means that it's going to be fixed configuration of charges, dq by dt equal to 0, current equal to 0. The main effect of VDS is it's going to produce a movement of the charges. So next we will see one sample charge configuration, okay, and then we will stop. Okay, we'll take one particular example instead of talking generally. Show channel charge configuration for, okay, a So we'll look at one particular condition, or maybe I'll actually add one more. VDS equal to 0.5, VDS equal to, we go in steps. So 1 volt and C. Okay, the reason why I added that will become very clear in a minute. So first, NMOS. Any physical this thing, so how to determine what is the device? Is it NMOS or there is only MOS? Okay, we don't have any other device in digital circuits. But is it NMOS or PMOS? That is most important because the on-off conditions are opposite to each other, right? So first you have to determine whether it's NMOS or PMOS. It is given as NMOS, and the number is also given for threshold voltage, and the gate voltage is also given. So first condition is okay. This condition you have to always check. Is it on or off? Now current is different thing. Current condition, if you want to see the value of the current or you want to do the current calculation, that depends on the VDS. Okay. But on off doesn't depend on VDS. On off only depends on one condition for NMOS transistor, is VGS greater than VT. If that is true, it is on. Okay. That is the channel has been formed. Charges are there. Now whether you move them or not, that depends on the value of VDS. So we will see it for 3 different values. Okay. So we'll start with the first one. Now we have to draw the channel charge configuration. That is what we are looking for. That is in the channel region. What is the charge under the gate terminal, that is the channel region, right? This is very important. What is the channel charge configuration? Now, directly, okay, I hope you can see this. This is the, okay, sorry, I didn't mark it. This is my source terminal. Assume again that it is grounded, and drain terminal, 0.5 volts. That is the question, that is part A. Directly, okay, you can see that I have drawn fewer electrons on this side compared to this side. Okay, what is the reason for that? Is the source side is connected to ground. Ground in digital circuits is the most negative voltage. Okay, electrons don't like that. They try to stay outside of the ground region as much as possible. But on this side, okay, it is slightly more. This is at 0, this is at 0.5. So if there are some electrons here, they prefer to go inside the drain region because it is at a slightly more positive voltage compared to the source region. So that is why in this side, okay, I have drawn fewer number of electrons. So this means that the electron concentration is going to be slightly lesser here compared to here. Here there are more electrons because all the electrons are attracted by the gate only. Okay, only thing is all the electrons that are attracted, all of them will be sitting here. Not